Great, thank you. Yeah, so today's lesson will be recorded and we'll be posting this up on YouTube. So if you're unable to follow along for whatever reason, don't worry, you'll be able to follow on later. But so this training can be held, you can either do this on your machine locally if you have Julia installed on your machine. But today's training, I'm gonna host it on JuliaHub. And it's gonna be free to log in to perform the training on JuliaHub today. So before we continue with the slides right here, what I want to do is go ahead and have anyone who's going to follow along, or this is important for the recording too, but please go to juliahub.com. We're going to set up the environment right here so some of the packages can install while I go over the slides. So if you go to juliahub.com, in the upper right-hand corner, you'll see this little person. Oops. This little person right here. Go ahead and click on this. And here, you'll be presented with a few different options to log in. I'm just going to stick with Google, but you can use GitLab, GitHub, your regular email address, LinkedIn, and so on. And if you don't have an account right now, the account is free to create, and you'll be able to use this, for free right now. So go ahead and log in with whatever account you want. I'm just going to use Google, use my juliahub.com email. Okay, so this is the JuliaHub platform. We won't spend a ton of time here, but I will give you an idea of what's kind of going on here. Here we are on the home page, the home tab. It gives us an overview of like the applications available to us, any projects that we've been working on, and any jobs that we currently have running in the background. Okay, there's also a few other tabs here. We can take a look around. If we go to the applications tab, we see some other default applications available to us. This is, of course, the free version of JuliaHub we're taking a look at right now. If you have your own instance for your own organization, you might see different applications and registered applications and so on. Like I said, this is the free version that you just logged into. We have notebooks also, Pluto notebooks, which are analogous to Python Jupyter notebooks. In here, we have an Ask AI capability, package manager, all the packages in the ecosystem. For example, in the upper right-hand corner right here, if I type in plots, I'll see the plots package from the Julia plots organization. Just pointing this out because plots will be one of the packages we use today. So if you're kind of curious like what packages are available to you on this platform, you can check out this packages tab. And a few other tabs here, we have jobs. Right now I have a Julia IDE job running. I'm going to stop this actually. But once you start up your project in a moment, we'll have jobs populate this list that are currently running. And then we also have some data sets and files at our fingertips. Okay, so today's lesson, we're going to keep it all inside of a project. Okay, so if you're following along right now, or if you're following along on YouTube, go ahead and click the projects tab right here. And what we're going to do today is we're going to create a new project. Okay, so here I'm going to go ahead and select generic project on the left-hand side. Just 4 steps right here. We're going to step through them, no big deal. For the name right here, I'm just going to name this Julia for Engineers. Julia for Engineers. And then for the default application in the lower right-hand corner, I'm going to make sure I have Julia IDE selected, the Julia IDE. I'll leave the rest, press next. I'm not going to change anything right here. I'm going to go ahead and press next. And I'm not going to change anything right here. So I'm going to go ahead and hit create. Should be able to done in just a moment. I getting this error? Looks like that was kind of weird. It gave me a little error, but it looks like the project created just fine. I'm gonna go ahead and hit connect right here. Okay, reset your workspace for this project. It's fine. Okay, I'm going to go ahead. So assuming that worked for you, you should end up on a, I'm just going to switch to a different project right now. I'm not really sure why this is giving this error. I think I might have named a previous project the same exact name. But for now, let's just go ahead. So assuming that worked for you, you can go ahead and hit the connect button. And you will be taken to a code space similar to this right here. Okay. I'm going to delete some of the stuff over here just so we can delete permanently. That's fine. And delete permanently. That's fine. Okay. So you'll be, I'm going to go ahead and zoom in here so you can see. So when that opens up, you'll see the Julia IDE open up right here, and you'll be inside your code folder, and like you'll have nothing populated right here right now, right? You'll have no files over here. So here, what I want everyone to do right now is install some of the package dependencies or the packages that we're going to need to use for this training, okay? And then I'll go back and see here after we look at some slides, and then we can take a look at what's kind of going on in here. But here in the Julia REPL right down here, I want you to hit, first we need to enter the package manager. So in order to enter the package manager, you're going to need to hit the close bracket sign. So go ahead and hit the close bracket key on your keyboard. It looks like this. And once you do that, you'll get a, you'll go to the package manager right here. Okay. There's a chance that this might say, so right now I am in the code environment for this folder, and that's correct. That's what I want it to be. If yours says like version 1.1 or something right here where it says code, all you're going to want to do is type in activate dot, so that we activate the code environment that we're working in right now. Okay? And then once you've done that, you should see code right here in your package manager. Okay, so here in the package manager, what I want you to do is, I'm just going to type it out, add for diff modeling toolkit, differential equations, and plots. Okay, I want you to go ahead and type in this command and hit enter. So what we're doing here is we're installing these 4 different packages into our environment so that we can use them during today's training. So this is going to take just a second if you've never installed these on your environment before. And of course, I haven't either because this environment is empty right now. And this is just going to take a second to install. Okay. So let's go ahead and go back to the slides, and then I'll kind of like decode what's kind of going on in this IDE in just a moment. All right. So all right. So let's start off with Julia. Okay. So what is Julia programming language and what does it aim to do, right? So with all the companies we've worked with and the programs we work with across various industries, including but not limited to aerospace, automotive, healthcare, robotics, and AI, regardless of how mature these organizations are, they all face the same obstacle. And that obstacle we call the two culture problem, right? So generally in the life cycle of a program, in the research and development phase, engineers and scientists, they generally prefer a high level, succinct programming languages that are expressive and allow them to perform research and analysis without having to focus on things like memory management and low-level programming details and optimization. So the idea is because of this dynamic, it ultimately leads them to languages such as MATLAB, R, or Python. Conversely, developers, on the other hand, they require performance, reliability, and scalability in their production environments, right? So because there's products are put into deployment and this requirement for high performance languages, this leads them to languages such as C, C++, and Java. Okay? But as we transition from the research and development phase into the production and deployment phase, a lot of the models and work that were done by the engineers in their programming languages need to be reworked in and deployed in a language that's suitable for use by the developers. So this ultimately leads to refactoring of models, friction in production, and in many ways, redundant work. So the idea is that Julia solves this two-culture problem by providing both ease of use and speed to scientists, engineers, and software developers. The idea is that modern language design and compiler techniques make it possible to provide a single environment that's both productive for engineers and efficient enough for deploying intensive applications. All right. And of course, all these statements are supported both by open source benchmarks and domain-specific benchmarks. If we kind of take a look on the right side right here, we have data from the Computer Language Benchmarks Game open source project. This is a project where a given subset of algorithms, the project is meant to compare how a given subset of algorithms can be implemented in various programming languages, and it measures how fast and how easy it is to solve those algorithms using these different languages. So if we look here in the chart, we can see that Julia occupies the coveted lower left-hand corner, in which the execution time is fast, and also the amount of code needed to implement these algorithms is low. If we take a look on the right side here, we have some domain-specific benchmarks. We have a rigid body system represented as a non-stiff ordinary differential equation. And we can see the Julia solution, specifically differential equations.jl, being compared to the speed of a few other solutions, Fortran, Sundials, MATLAB, and the Solve. And we can see that for any given acceptable error level, the Julia solution here in green is anywhere between 1 to 2 orders of magnitude faster than any of the competitors. All right, so let's go ahead and get our hands dirty and start problem solving with Julia right now, okay? So here we have a foundational engineering problem, if you will, called a mass spring damper, okay? So for our system right here, we have a spring at the top, and we have a damper also connected to that spring at the bottom. On the left side, we have a constant force being exerted on this spring and damper. And what we want to know is the value of x over time. We want to know how fast or how much this spring gets compressed over time, given the known quantities of force, spring constant, and damping coefficient. Okay, so we represent this entire system with this governing equation right here. D times x dot plus k times x is equal to F, right? So F right here is simply the force. Then we have D times, I'll cover this one first. We have k times x, which is the force that the spring exerts against the force. So k is just the coefficient of the spring, and the x is the amount that the spring is compressed. And finally, we have the force that is given by the damper right here, which is d times the derivative of x. In other words, d times the rate at which the spring is compressed. Okay, so now that we have this sort of like background for how we're going to try to approach and solve this problem, let's go ahead and implement this in Julia. Okay, so I'm going to go ahead and put this to the left side right here. And I want to go ahead and bring up JuliaHub. Okay. This. So it looks like my packages have finished installing inside my REPL down here. I can see, so that's great. So I have a few things I want to point out today. So you probably all received an email. You should have received an email just before this training containing these three files. Here, I'm gonna zoom in right here. So the first file, this part one solution file, is simply the solution to today's training. So I kind of want you to open that up as you follow along because there's going to be, if you're falling behind on typing anything, you can copy and paste from the solution file. Okay. This project and manifest file, I'll explain a little bit more right now, but the project file are all the package dependencies that our solution relies on, the direct package dependencies. And then the manifest file are all the indirect package dependencies that we're going to be using for today. So all this right here, you don't actually need to bring into your Julia IDE environment. I just want you to have this as a backup, just in case. Okay. And Sanjeev, if you could send everyone that GitLab or GitHub link that I just sent you, that would be really good. You should see inside of the chat right now a link to this right here. And so this GitHub gist it's a link. You don't need to log in to look into this, to access this or anything, but in this link are the same exact three files just in here, if you'd rather access it through a link as opposed to opening up any files. So right up here, we have that same manifest file, the indirect dependencies I just mentioned. If I scroll down quite a few lines, about 3,000 lines, I'll see the second file is that same solution file that I just mentioned. So you can also copy and paste from right here if you'd like. And at the very bottom, we have the project file, which are the direct dependencies for this training. So like I said, this is just here for reference. You don't need to do anything with these files other than maybe just have them handy so that you can copy and paste. All right. So if I go back into my JuliaHub page here, I'm in the Julia IDE. Here we can see that all the packages have installed. So right here in my Julia REPL, I'm still inside the package manager. If I type the word status, I'll see that, hey, look, now inside my project TOML file that was just created, see, there's a new project TOML file that was just created. Here are all the direct package dependencies that we have. And these are the ones you just installed. Okay? So you open up this project TOML file on the left side, you should see all these dependencies that you just installed. Okay? So now these are all what we call the direct package dependencies that we're currently using. These packages actually depend on other packages, right? These packages have their own set of dependencies. And those set of dependencies, what I'm going to call indirect dependencies, you can find them in the manifest TOML file. All right, so if I open up the manifest TOML file, I can see all the packages that my project TOML packages depend on. All right. So the idea here is if you are working on any kind of code and you want to hand it to like a coworker or someone else to run your same stuff, it's probably a good idea to hand them your project file and your manifest file so that they are running the code using the exact same package versions you are. So this is kind of why I handed everyone these files, just in case you have any trouble with installing or anything like that, you have the full solution at your fingertips. Okay, great. So now I'm going to go back into here. I'm going to, let's see, I'm going to close these files up here. I'm going to exit my package manager and go back to the normal Julia REPL by hitting backspace right here. Okay. And then I want everyone to go ahead and create a new file, and you can call that file part1.jl, part1.jl. All right. I already have part1.jl, so I'm just going to use this one right here. And I'm going to start with it empty. So you should have a part1.jl right now, which is completely empty. And in the REPL, you should be at the Julia interface, not inside the package interface anymore. Okay. Okay, so let's go ahead and start going. So we've installed all these packages inside our environment, but we need to import them into our code in order to use them, similar to import statements in Python or other languages. And remember, you can copy and paste everything I'm doing right here. So if you decide that, hey, I don't want to type along with him, you can just literally copy and paste it to follow along, okay? So I'm going to type in using forward diff, using modeling toolkit, using modeling toolkit again, and I'm going to import a T no units object, and I want to call it T. I'll explain what these are in part 2 when we start to use them. And I'm going to import an object D no units, and I'm going to import it as D. So I'm going to be able to reference it as simply using D or T. Using differential equations. And lastly, using plots. All right. So you can execute code two primary ways. You can just execute it straight from the file, or you can do things from the REPL. So for example, if I were to click in the REPL down here, I can just say something like QQ equals 1, right? And I can just start to do math down here, no problem. But if we want to run any of the lines of code in our file, all we have to do is put our cursor on that line and hit Shift Enter, okay? So I'm going to put my cursor on the very first line here. I'm going to hit Shift Enter. And then you see inside the REPL that using forward diff is executed. And you see this little check mark once that line of code is done executing. So what I'm going to do is I'm going to continue to use Shift Enter so I can import or execute all of these statements. All right, so now that that's done, we're doing part 1, right? Let's go ahead and start modeling this out. So so you can do pound signs for comments. And I'm just going to call this part 1, solving with Julia. Okay, so the first thing we're going to do is we're just going to go ahead and define the constants in our system over here, right? The knowns. So we're just going to call these, give these names. So I'm going to say D is equal to 1, K is equal to 1,000, and F is equal to 100. I'm going to execute all these statements. And then we're going to solve this system for the first 10 time steps. And we're going to say a single time step is 0.00 seconds. Okay, so I'm going to give that time step a variable name. I'm going to call it delta t. Okay, delta t. So inside of Julia, we're able to use Unicode. So I'm going to go ahead and do that right now. I'm going to type in backslash delta. And I'm going to select the delta with a capital, so the capitalized delta. You can hit enter, or you can just click on it. And now you have a delta symbol, and then a T, and then space. All right, so Julia is going to be able to recognize delta T as a single variable. And right here, I'm going to do 1e to the -3, 1e to the -3, and shift enter. All right, so it's pretty cool, right? We can use Unicode here. So in the REPL, if I type in backslash delta tab T and press enter, I can see that the system recognizes that as its own variable. Okay, so what we're going to do here is we're going to try to solve this for the first 10 time steps. Okay, so let's go ahead and create an empty array to store our answers. So we're trying to solve for x, right? So we're going to do x is equal to zeros 10. And all that does is it's going to create an array of size 10, and each of those indexes are going to be filled out with 0. Okay, so for this part one, we're going to be solving this system using two specific mathematical techniques. We're going to solve it using finite differencing derivatives and Newton's method to approach our solution. So the ins and outs of both of these methods are pretty mathematically involved, or are definitely outside the scope of today's lesson. But let's go ahead and code it up, and I'll talk to it as we go through it. Okay, so first thing we're going to do is we're going to write a function called f. So I'm going to type function f, and this function is going to take in two arguments. The first one is going to be x sub I. So I'm going to type in x, then I'm going to use Unicode here, \_ I. So x \_ I, and then I'm going to press enter. So then now you can see here we have this little x sub I as a single argument or a single variable. Comma, and then the second argument here is going to be x sub I minus 1. X sub I minus 1. So I'm going to type in x, and like pretty much every time you want to do a Unicode type thing, you're going to do the \. So it's going to be I minus 1 in the subscript. Okay, so we have to do each of those one at a time. So it's going to be \_ I, enter. Then I need a minus. So now it's going to be \_ minus, enter. And then now I need a 1. So it's going to be \_1, enter. And I'm going to hit enter here and put an end at this end of this. So the idea here is this function is going to take into a position x as well as x, the previous position. Okay, we haven't really explained what's going on here yet. So that's all we know so far. So let's define the derivative of x using finite differencing right here. So I'm going to type in x dot I, so x \, and then subscript I, so \, I. So we're going to say that the derivative of I is equivalent to, I'm going to do x sub I minus x sub I minus 1 divided by delta t. Okay, so we're saying here the x dot is equivalent to this value right here, and that kind of makes sense, right? The derivative of x is equivalent to the change in x over the change in time. So this right here is the finite differencing derivative. Okay, so now let's represent the left, or the left and the right side of these equations in variables. Okay, so I'm going to type in LHS for the left-hand side of the equation, and I'm going to express this right here. So LHS is equal to D times X dot sub I plus K times X sub I. And then RHS, meaning the right-hand side, is equal to F. Right? So the left-hand side is right here, and the right-hand side is right there. So now what we want this function to return is we're just going to return the left-hand side minus the right-hand side. All right, so what does this, and I'm going to put your cursor anywhere in the function and do a shift enter to create that function. Okay, so what is this function doing here? The idea is this function ultimately returns the left-hand side minus the right-hand side, right? So if this value is true, what does that tell us? If this value is 0, right? If this goes to 0, what does that tell us? So if this function returns 0, it means that the two positions you put in to the function adhere to the dynamics of the system, right? Because in this side, the left side is equal to the right side. So if you subtract one from the other, it must equal to 0. So that's kind of what's going on right here, right? If we know that this function is returning 0, we kind of know that the positions we put into the function are correct. So let's see what I mean by that. So we're going to say the initial position of x is just going to be 0. Okay, when this force starts coming on to this spring damper, it hasn't moved yet. So x sub 0, or the initial position is 0. So I'm going to go into my Julia REPL right here, and I'm going to, so Julia starts indexing at 1, not 0 in their arrays. So I'm going to do x 1, and that's 0. Okay? And that makes sense because we set everything to 0, and that's fine. So now we want to know, okay, well, what is the second position for this system? So what we can do is use this function to help us find that second position. So what I can do right here is I can do f, and let's say I think the next position will be at 1. So I can put in 1 where I think the next position will be, and I put in its previous position, which is x sub 1, in other words, 0. So if I type this into the REPL, I see that, hey, my function returned a non-zero number. Therefore, my guess of 1 is not correct. I can guess again. I can do f of, how about 0.1? Okay, it looks like 0.1 is a little bit closer because my function is returning a smaller number. And through a series of guessing and testing, you can ultimately find out the value that returns a 0 is 0.05. So that tells us, hey, one time step into our dynamics, we're going to have compressed a distance of 0.05. All right, so that's kind of what this function means. So let's, instead of guessing through this like I just did right here in the REPL, let's use Newton's method to inch our way closer toward, or to systematically get to the correct answer for our 10 time steps. Okay? So the first thing I'm going to do here is I'm going to define a tolerance, 1e to the negative 3, meaning how close do I need to be to the final answer for me to be like, okay, I'm done, that's acceptable. And we're going to write a for loop right here to solve for all these positions. So we're going to do for I equals 2 to 10. And we're doing 2 to 10 right here because the first index, right, the first index has already been solved for. It's just 0. So we only need to solve for index 2 through 10. And so this part's going to be a little tricky here. But what we're going to do is we're going to redefine this f function in this each time we go through this for loop. So I'll just go ahead and type it out. So g of x sub I is equivalent to f of x sub I, comma, x I minus 1. Okay, so what's kind of going on right here? What we're doing is we're saying, hey, g of xi is the same thing as f of xi, but in the second argument, that argument is going to be a constant as opposed to some kind of variable, right? Because when we go through this loop right here, x minus I, x of I minus 1, this evaluates to a constant number. Okay, so right here, we're just kind of redefining the f function so that it only has one argument with it. Now we're going to do another variable called delta x equals infinity. This will make a little bit more sense after I write this next for loop right here. So I'm going to do while the absolute value of delta x is less than the tolerance we specified, delta x is going to be equal to g of xi divided by the forward, but by the derivative of gx of I. And then we're going to take that delta x and we're going to increment our solution a little bit closer to the final answer. All right. Okay. So this right here, this right here is Newton's method. So I'm not going to cover this in detail, but the idea here is that we have a tolerance, and each time we run this right here, we get a delta x, which inches us a little bit closer towards our final solution. That's why we're incrementing the solution right here. And what we're saying is so long that as the delta x right here is greater than whatever our tolerance is, just keep going towards, keep looking for the solution until we're within tolerance, then stop. All right. So I'm going to go ahead and run these lines of code. I'm going to run the tolerance. I'm going to run this for loop. It's done. So now I'm going to just plot my solution, x. So now, well, actually now in the REPL, if I type in x, you'll see that this, that x is now not only just populated with zeros, but it has all the other solutions to all 10 time steps. And hey, look at that second time step is 0.05, just as we thought it would be. And we can also plot the solution by running just simply plot x, plot x. And then we get this nice little plot right here with all our time steps in the x-axis and the position of x in the y-axis. Okay, great. So that is it for the Julia solution. Let's go back to the slides. Well, yeah, that's it for the Julia solution. Let's just kind of take a look at what we did here. All we did was we defined some of our constants, set up an empty array, set up this function that returned the left-hand and the right-hand side using finite differencing, and then we implemented Newton's method with this little for loop right here to end up on our answer. Okay, so let's go back to the slides right now. So that was part one, solving with Julia. So now let's move on to modeling toolkit. So modeling toolkit.jl is an open source Julia package designed for numeric symbolic computing, right? It provides symbolic computation, meaning we can represent our models using symbols as opposed to simply just variables and numbers. And we'll see that once we get to the hands-on. There's model simplification, meaning modeling toolkit simplifies our models and equations that we hand it so that it more efficiently solves the systems. It can do automatic differentiation, has code generation. We'll be using some MTK macros in just a moment to simplify what we actually have to type in. And modeling toolkit is very interoperable because not only is Julia language itself is open source, modeling toolkit is fully written in Julia, therefore it's fully composable with the open source Julia ecosystem. All right, so let's go ahead and try to solve this exact same mass spring damper system, but we're going to solve it using modeling toolkit. And you'll see that the code that we need to enter to solve this is not only brief, but it's pretty intuitive too. All right, so let's go ahead and go back to the Julia IDE right now. I'm going to drag this over here just because I only want to have one window pane open. So I'm going to just drag this over here. If you want to bring it back to the left side and split the screens again, you can just drag something to the far right side, no problem. Okay, okay, I'm going to copy this right here, paste it down here, and this I'm going to call part 2, solving with MTK. Okay, so remember earlier up here, we imported these things called T node units as T and D node units as D. Okay, so like what's kind of going on up here? So these are what we call symbols. So in the REPL, let's play around a little bit. So go ahead and use this. There's this type of command that tells you what type the argument is that you pass to it. So for example, if I do type of 1, I get, hey, that's an integer. Type of 1.0 looks like that's a float. Type of x looks like that's a vector or an array. Okay, but if I do type of t, let's see what I get. I get a number. And if I do type of d, what do I get? It's some kind of differential. So these two items right here, this t and this d, these are symbols, okay? this is how we're going to be able to symbolically represent our system using these symbols. Because when we use T and D, for example, it doesn't evaluate to a specific value, right? Like if I were to type in K, it evaluates to a very specific value that we defined earlier. But if I type in T, then I just get T back. If I type in D, I just get D, or this differential thing. So these are symbols. And we'll see how they work as we build up our modeling toolkit model. But you can also see down here, we can do stuff like this. Like, for example, sine of T. If I type that in, it just returns sine of T. Well, how about let's use our differential to see what the derivative of sine of t might be. So if I do d of sine of t, I get this guy right here, which, isn't the derivative of t the cosine of t? Well, we can expand this out to be a little more human readable. So we can type in d of sine of t, then I can do this vertical bar arrow and expand, vertical bar arrow, and I can do expand derivatives, and I can see that, hey, the derivative of sine of t evaluates to cosine of t. So I just wanted to show you kind of like how these symbols differ from just normal variables real quick, and then we'll see a little bit more of the magic happen right now. Okay, so what we're going to do is we're going to build up an MTK model to solve this system. And we're going to use some MTK macros to reduce the amount of code that we need to type in. So I'm going to type in with this @ side MTK model. I'm going to name my model simple MSD because it's a simple mass spring damper. And I'm going to type begin. And within this macro, I'm going to use 4 other macros. So I'm going to type this out. So first, let's go parameters, space, begin, variables, space, begin, components with an S, components with an S, begin, and equations, begin. Okay, so this is sort of like the boilerplate code you're kind of want to use when you start building up any kind of MTK models. In the parameters, we're going to put in the parameters of the system, what we know. In the variables right here, we put in the variables in the system that we want the system that we need to solve for. Components, you don't need to worry about for this part. We'll play more of them in part 3. But this is kind of how we can have a hierarchy of different models and components integrated into each other. And then equations, this is where we put the equations that govern the physics of our system. All right, so let's go ahead and fill out each of these fields. So first, in the parameters, I'm going to type in f equals 100, d equals 1, and k equals 1,000. All right, these are the parameters of the knowns in our system. In the variables, so this is going to be a little unique. I'm going to do x of t is equal to 1.1 or 0.0. And then the second line, x dot t equals f over d. Okay, so like I said, these variables, x and x dot, these are what we're trying to solve for in the system. And the system is going to simulate it with respect to t. And so what are these? And these are over here are the initial conditions for these variables. So this one right here, we're saying the initial position, it's just going to start at 0. So this spring is just going to start uncompressed. That's straightforward. And then we're saying the initial value for x dot is f over d. Well, if we look at this equation right here, we know that initially x is equal to 0. And if that's 0, we can divide both sides by d. And then we get x dot is equal to f over d. So that's the initial value for x dot, right? Initial value for x dot is f over d, and that's what we have over here. Then finally, like components, not relevant for this one part. And then finally, we have equations, the equations that govern our system. So first, let's go ahead and type in this equation. Is d, I'm actually just going to copy it from up here so I don't have to type as much. Actually, that's a little dangerous. I'm not going to do that because this has subscripts I don't need. I'm just going to retype it right here. So I'm going to do D times X dot plus K times X tilde F. All right. So this right here is simply this equation. So that's pretty straightforward. It doesn't matter. So this, notice that we're using a tilde right here, right? So normally in programming languages, such as Julia, for example, whenever you use the equal sign, that's an assignment, right? We're saying, hey, the thing on the left needs to be given the value that's on the right. That is not what we are doing right here. What we are doing right here is we are saying this is an equality, and whatever x and x dot are, regardless of what they are, this equality must hold true. Okay, so this is what we're talking about, like sort of symbolically representing our systems. This statement will not be executed as an assignment statement or anything like that. It's an equality that the system knows about and that it's going to hold true throughout its entire simulation. All right. And now there's one more equation we need to give to our system. So we notice right here, we have two variables, right? We have x and we have x dot. So what is x dot, right? X dot is the derivative of x. However, Julia and MTK doesn't know that. It doesn't know that there's that relationship exists between these two variables. It doesn't know that, oh, this dot means that it's a derivative of some sort. This is simply a Unicode variable name that we gave to this variable. So we need to tell MTK that, hey, the x and x dot, they have a relationship in between them, okay? And we can define that relationship right down here. And that relationship is pretty much as simple as you think it is. We're going to use our symbolic differential, d of x tilde x dot. That's all it is. We're just saying the derivative of x is equivalent to x dot, right? So like I said, these are the equations, the physical equations which govern your system. And that's where you put them right down here. And that's it. That's all we have to do for MTK model. So I'm going to do Shift Enter to run this right here. I am going to build up the system. Okay, yeah, I'm going to build up the system using another macro, MTK build. And I want to call my little system that I build simple underscore MSD. And that's going to be equal to, that's going to be an instance of the simple MSD MTK model up here. So if you're kind of wondering what these macros do, these macros, when Julia sees this macro, what it basically does is it takes all the code after that macro and it formats it in a way that's ingestible for MTK. So that a lot of that, well, most of that happens under the hood. So it kind of abstracts that away for us. So we only have to specify the things that are of interest to us as engineers. But here, I'm going to build up my MTK model. Then I set up a problem for this model. So I'm going to call it prob equals ODE problem. I'm going to supply that model that I just built. This second argument is going to be an empty array. If I wanted to modify any of the initial conditions, I would modify it in this array right here, but I don't have any modifications I want to make. So I'll just leave it as is. The third argument right here is going to be a tuple, and it's going to have the time span that we want to solve our system over. So we're going to go from 0.0 seconds to 0.1 seconds. And that's going to be the same time frame that we solved in part one. And then the final argument is going to be an empty array. If we wanted to modify any of our parameters, we would modify it in this argument. So I'm going to go ahead and set up this problem, Shift Enter, and I'm going to solve this problem. Shift enter on the solve. And then once that's done solving, I can go ahead and plot. So I'm just gonna, what I'm gonna do is I'm gonna plot the solution. And this is pretty cool right here. We can decide what in the solution we want to plot. So I'm gonna index into the solution. I'm gonna do IDXS equals. So the first thing I'm gonna wanna plot here is let's plot the X variable. Okay, so how do we access X? So we know that X is sort of like a variable or property of this simple MSD model. And we know that the model we actually built, this is an instance of the simple MSD, right? So we can access our X through this symbolic object right here. So what I'm going to type right here is I'm going to type in simple underscore MSD dot X. And that's all I'm going to type. I'll give the labels something to look at. Y label equals, let's call this X. Shift enter. And here we have our solution. And the solution, you'll notice that this solution is the same solution as the one in part one. So if I press this little arrow right here, this is, of course, a little more coarse because this did it, part one, we solved at 10 distinct time steps, whereas the solution part two, it was a little more smart and it solved for more time steps in between and gave us a better fitting curve. All right, if I want to plot, let's say, the derivative of X, I can also do that. So I can just copy this line right here. And then now, instead of indexing into X, I index into X dot. And I can shift enter that. So now not only do we have X, but we have X dot. And the last thing I want to show you here is it's pretty cool. We can actually index, do some logic in our indexing. I'm just going to copy and paste this quick one. Right, so let's say we want to know the spring force, right? The spring force is K times X, right? That's what the spring force is. And then the damping force is D times X dot. But we don't have the spring force or the K force or the damping force anywhere in our parameters or variables. But what we do have are the components to calculate the spring and damping forces. So we can just simply use those components, okay? So for the spring force, we know that it's going to be K times X, right? So we're going to index into K, and then we're going to index into X. So right here, line 74 right here, you can see that in the index, all it's doing is it's indexing in and saying, hey, I want you to plot the product of X times the product of K. And then we label that spring force. Similarly, we can do that for damping force too, right? We can say, hey, I want you to plot the damping force, which is X dot times D. So I can go ahead and plot this, the spring force, and I get this nice little curve right here, and also the damping force, this nice little curve right here, and I can plot the spring force and the damping force added together. And of course, as expected, the sum of those two is 100 because that's how our system was defined. Okay, so that's it for part two here. In summary, what we kind of just did right there was we looked at our mass spring damper system and we modeled it using Modeling Toolkit simply by specifying the parameters, the variables we wanted to know, and the equations which govern our system. And that's all it is. All right. This was a lot easier than trying to understand finite differentiating derivatives or Newton's method, right? Okay, so let's move on to the final part here. Where are my slides? All right. Okay, so there's a solution with MTK. All right, so let's move on to this idea of component-based modeling and also causal versus a-causal modeling. So causal modeling is the idea that relationships are defined in our systems are defined based on how variables affect another. In other words, you might have something such as y of x is equal to 3x plus 6, right? The way that this is formatted, we kind of understand that y is the output here and x is the input. So x kind of drives y, if you will, based on this. So, whoops. So whenever your model varies, like any changes in your design or your workflow, you need to generate new system mathematics and generate new model functions because you need to organize everything in your systems so that outputs are on one side and inputs on the other, right? Because relationships are defined that way. In a-causal modeling, however, relationships are specified without or defined without specifying the direction of influence. Sort of like how we defined this equation right here. We didn't say x drives x dot or x dot drives x or anything like that. We simply wrote down this equation that depicts the relationships, and we gave that to Modeling Toolkit. That's it. We didn't say one's a function of the other. And by designing our systems through this a-causal modeling lens, it enables component-based modeling. The idea that you can model your components, for example, maybe I want to model a spring, and then separately I want to model a damper, and then separately I want to model a mass. I can then connect all these together in a component-based type of workflow. And whenever anything changes inside of my models, rather than having to generate entire new system mathematics, I can simply just change whatever I need to change within the components themselves, or change the connections as needed. Okay? So let's go ahead and take a look at a problem with component-based modeling, and we'll get a better idea of what's going on here. So what we're going to do today is we're going to create a suspension system. Okay? What we're going to start off with is we're going to create mass, spring, and dampers. And then those three components are going to make up the mass spring damper. And then in order to create our suspension system, what we're going to do is we're going to have a seat, which is instantiated as a mass spring damper, MSD, sitting on top of a car body, which is another mass spring damper, sitting on top of a wheel, which is another mass spring damper, sitting on top of a road, right? So the idea is we kind of have three mass spring dampers sitting on top of each other, representing a seat, car, and wheel. And then at the bottom, we kind of have a road here. And the road may have bumps, and we kind of want to know, as this seat, car, and wheel travel over this road with bumps, how does the suspension system look? Like, how do the seats like bounce up and down? Do they stay perfectly still? What are the dynamics of the system? So that's kind of what we're trying to investigate right here. And I'll be using this diagram to kind of help orient us of what's going on as we start to build up our spring, our damper, and our mass, as well as the connection points. In other words, ports or flanges around them. All right, so I'm going to go ahead and move this to the right side. And so for this part 3, we're not going to do any typing at all. I'm going to recommend that you copy and paste the entire thing, and I'm simply going to talk through the code and we'll execute it together. Okay, so I'm going to go ahead and look for my solution. There it is. And I'll paste it right down here. Okay, so part 3, component-based modeling with MTK. So let's just go ahead and go through each of these lines of code and let's start figuring out what's going on. So the first thing we need to do right here is build a connector, right? I just mentioned earlier that there's these things called ports and flanges. So you can kind of think of connectors as how we connect various components to one another. So we might have a mass component, a spring component, and a damper. We need to use connectors to connect them together. Okay, so this connector has two types of variables. a cross variable and a through variable. Okay? So the idea is if two components are connected to get each other with a mechanical port, their velocity at that point must be the same. Okay? That's the definition of a cross variable. So whenever two components are connected, their cross variables must be the same. Right? That makes sense, right? If your two things are physically connected to each other, it implies that when one moves, the other one moves. So their velocities are the same. And then our connectors have a second type of variable, which is what we call the through variable. And the through variable, rather than all the connection points having to have the same value, but instead the sum of the force at all the connection points must sum to zero. Right? So if there's two things connected at one given point, all the forces acting on that given point must sum to zero. So I'm not going to spend a ton of time on the cross and through variable theory, but we'll make sure to send out this link afterwards with a follow-up email. And here in the Modeling Toolkit Standard Library JL documentation page, it talks a little bit more about through and across variable theory, how you can determine what is appropriate for your through and across variables, depending on what domain you are working in. We, of course, are working in the translational domain. So that's kind of why we see force and velocity as our across and through variables here. But that'll make a little more sense as we start connecting together. So I'll move on to the next one thing right here. So here we have an MTK model for a spring. This spring right here has a parameter k, variables. So the first variable is delta S, which is going to be the distance at which the compression of the distance the spring experiences, and F right here, which is the force that the spring experiences. The spring is going to have two ports. It's going to have flange A and flange B. In other words, port A and port B. And these ports, if you look at the spring right here, these ports are on the left side and the right side of the spring. All right, it's going to allow us to connect to other things. So what are the equations governing our spring? Well, we know the force is equivalent to K times delta X. So that's that. This second line right here is saying, hey, the derivative of delta X is equivalent to flange A dot V minus flange B dot V. So what does that mean? What it's saying is, so delta S is the compression that the spring experiences, right? So the derivative of delta X or delta S is simply the speed at which the spring is compressed. Well, what is the speed at which the spring is compressed? It's simply the difference in between the speed on the left side of the spring versus the right side of the spring. So the difference in these two speeds right here, like the left side and the right side of the spring, that dictates how much the spring is compressing or how fast it is. And then lastly, we have these force right here. Okay, so there's a little bit of an art to determining the correct signage for these, but let's see here, expand this a bit. So let's say we take a look at the right side of the flange or of the spring, so flange A right here. So the way to determine what sign is appropriate for this is, first of all, first you look at the port, and then you draw the across variable in the positive direction. So remember, our across variable is velocity, and the positive direction of that is to the right. And then you draw the through variable, entering the component on the side you expect it to enter. So here, the force is also entering from left to right. So because these two arrows are pointing the same direction, we know it's a positive F right here. So this is one way of determining it. Okay? Conversely, or contrastingly, port B, if we draw the cross variable in the positive direction, that's to the right. But here, the force is entering from right to left. And because these signs are in opposite directions, we have a negative F. Okay? I won't spend much more time on that, but yeah, there is a little bit of art to making sure you get this right. Here, We have a damper, which is defined very similarly to the spring. We have a parameter d. We have v, which is the velocity the damper experiences, compression velocity. F of t, which is the force the damper experiences. Just like the spring, we have a flange or a port on both the left and the right-hand side. And we have equations that define the dynamics here. We have the force is equivalent to the damping coefficient times the velocity. We have the velocity at which the spring or the damper compresses is the difference in the velocity of the left side of the spring, the A side, and the right side of the spring, or the left side of the damper, which is A side, and the right side of the damper, which is the B side. And we determine these forces in the same exact way we determined it for the spring up here. All right, so now here's our mass. Our mass is going to have a few parameters: mass, gravity. The variables we're interested in is the position, the velocity, the acceleration, and then the force that mass experiences. Our mass here is only going to have one flange. It's not going to be on the left or right side of this mass. You can just kind of think of it as representing the center or the entire mass itself. And here are the equations which govern our system. So the mass times the acceleration the mass experiences is equivalent to the force exerted on that mass, as well as the force due to gravity. Here are our standard derivative equations: the derivative of velocity equivalent to acceleration, derivative of position equivalent to velocity. And then we have definitions for F and V for our mass. Okay, so now that we built up these three like mini components, if you will, spring, damper, and mass, we can bring them into one big component, which is this mass spring damper right here. And you'll notice that before we might have we use MTK model macros, and here we're using a component macro. The main reason for that, the only reason for that is inside of our mass spring damper, I'm going to use some initialization equations. And right now, the MTK model macro is not yet able to handle this type of initialization equation inside the model. So basically, for now, we're just going to use the component function instead of the MTK model macro right here. But rest assured that they are the same. Okay. So just like before, we had parameters, variables, components, and equations. We're also going to have parameters, variables, components, and equations. So here inside our mass spring damper, we have parameters: mass, gravity, stiffness, damping, and initial position. And then we have these other systems or other components that make up the mass spring damper. So we can see here that the mass spring damper is made up of a body, which of a mass that we're calling a body. It's made up of a spring, we're calling a spring, and it's made up of a damper, we're calling a damper. And then this mass spring damper also has a port on the mass side and a port on the SD side. So if you kind of think of this whole entire thing as a mass spring damper, we can kind of think of the port M is on this side, the left side on the mass side, and then port SD is on the spring damper side. Okay, so you remember earlier we said that, hey, these across variables need to be the same at any connection, and the through variables must sum to zero. So like, where is this enforced? Like, we haven't really showed how this is enforced. So we do that by actually connecting components together using, so I'm in the mass spring damper right here, using these commands, the modeling toolkit connect commands. So here, what we are saying is, hey, we want to attach the port on the SD side to the spring flange B and damper flange B. So these are all being connected to each other on this side. And then we also want to do the port on the M side with the flanges on the A side and the body flange. So these ports will all be connected to each other. And then that's when the across and through variable constraints will be enforced. And then lastly, this initialization equation, what this is doing is it's basically reaching into the body, which is the mass, and it's saying, hey, the S the initial position for S, or the initial value for S, should just be this initial position variable, which is this right here. And then we have this return statement because we're using the @component macro as opposed to the MTK model macro. All right, so that's what the mass spring damper is. So I'm going to go ahead and execute all this stuff that up until now. So the connector, the spring, the damper, the mass spring damper. And then I'll build this up. I like to just kind of build the model that you just did to make sure there's no weird errors that come out. And then, okay, let's continue on. So now that we have that mass spring damper, we're going to build the components necessary sort of like for this road right here. So we have these two other connectors. We're calling an input and an output connector. And these, unlike the mechanical connector we used before, where it had that across and through variable, these connectors we're simply going to use to pass information in between components. So one component is going to have an output, and another component is going to take that output in as an input. Okay, so let's take a look at this MTK road data. This model right here, this road data, is simply information for the characteristics of the road. Okay, so it has this output component, which is an instantiation of a real output. It has some parameters, and it has all these equations going on right here. Right, so basically what's going on is it's going to take these parameters, it's going to run these equations, and those equations are going to represent the characteristic of the road. Then all that data is going to be put into output. So all this road data is going to be put into this output. Yeah, into this output. And then later we'll see something else connected to the output in just a moment. So now that we have the road data, we build up the road itself, which has a physical connection, which we can connect to the wheel, which is like the bottom of our car. This takes in an input, and it's saying, hey, the derivative of the position of that input is going to be the velocity of the road. So the idea here is the road data up here is going to output data, and we're going to connect it to the road itself. Okay, so I'm going to go ahead and run some of this code. And here's our system that we built up. So we have a wheel system that consists of a mass spring damper, a road, and the road data. At the very bottom, we have the road data's output connected to the road. And then, hold on just a second. Yeah, so we have the road data connected to the road, and then we have the road's mechanical connection connected to the mass spring damper or the wheel. So I'm gonna go ahead and run this, build our system. And here we can, earlier in part 2, we didn't modify any of the initial positions, but here I want to show you how you can modify those initial positions using this right here. We know that wheel sys is the name that we gave to our system, and we know that a wheel system has a wheel that we can access. And we know that every single wheel is an instance of a mass spring damper, and all mass spring dampers have an initial position. So that's kind of what's going on in this symbolic representation right here. So I'll execute this, set up the problem, right? Wheel sys, this is the time we want to solve over. These are the modifications to the parameters we want to give to the system. We'll solve that system, and then we'll go ahead and plot it. So here, we're able to index into our solution just like before. And what I'm going to do is I'm going to plot the road as well as the body's position. And there it is. So we see the road here in blue. We see the little bump, and those are characteristics determined by some of the parameters in our road. And then we see the wheel body right up here, like going over the bump, and then it has this little oscillation response that comes afterwards. Now, of course, these responses will change depending on the characteristics in your spring and your damper. All right, we are almost there. So we built this quote unquote wheel system, which has a wheel in the road. But remember, what we want to do is build up the entire, not just wheel and road, but we also want to have a car body and a seat on top of that wheel. So how do we do that? We're going to go here to MTK model system. And if you notice, this is actually the same exact definition as the wheel model with the addition of these 4 lines. Right, so all we did here was we just said, hey, we need a car and a seat in our model. Okay, bring them in. And then let's just make sure that the car body is properly connected to the wheel. And then the car body is also properly connected to the seat. We can do that, execute that, build up the system. Here, we can change the initial position for the car, seat, and wheel to be different from one another. I'll execute that, and I'll go ahead and plot everything. And then here we see our system with the response. We see the road on the bottom, the response due to the wheel, the response to the car body, and then the response due to the seat. And you can see how these responses are all kind of similar and characteristic. And that makes sense, right? Because they all have the same damping and spring characteristics. If I were to change some of them, let's say I go ahead and change the seat stiffness and the car damping to something else, we'll see that we end up with very different responses across each of the components. Okay, and that's it. So let's go back to this. Yeah, okay, so we're all done. So in summary, what we did today was we first solved this mass spring damper problem using Julia. We used finite differencing and Newton's method. We then moved on to modeling toolkit, and we saw how we could solve the same problem using these simple macros to solve our systems by supplying equations, variables, and parameters. Then we took a look at what a-causal modeling and causal modeling was, the differences, and how they relate to component-based modeling. And then what we did was we simply took a look at the code to build up mass spring dampers and bring them all together into a suspension system, which highlights or reveals the dynamics of a car moving over a bumpy road. And so the last thing I want to leave you with is a preview for part 2 of Julia for Engineers. We haven't scheduled this out yet, but most likely it will be sometime in November or December. And in this training, we're going to take a little more deeper dive into some modeling. We're going to model an actuator right here in the orifice. We're going to see kind of what kind of pressure is put on this system given the areas and pressures in the fluid dynamics here. Okay, and with that, we have a few minutes left. So thank you everyone for joining today and paying attention and all that. We'll make sure to send out some follow-up emails with some relevant information and files for you to, do all this on your own. And I'll be hanging around here for another maybe few minutes. So if you have any questions, just go ahead and let us know. Thanks a lot, everyone.
Yep, you can type in your question in the Q&A section and we'll answer them in the order we receive them. There's one question that has come in. What about ML workflow? Right, David?
Sorry, what was the question, Sanjeev? Can you read it again?
Yeah, you don't have a name there. There's written, what about ML workflow?
What about ML workflows? So that is not something that was covered today, but let's see here. Let me get some slides up real quick. Yeah, so this was not something that was covered today, but if you are interested, please reach out to us and I'd be happy to like get some time with you and give you a full presentation on this. But we also have so we have this thing called SciML, which is the idea of scientific machine learning, combining data with models. And we have a nice little demo and presentation on how we can go through and model sort of like a rocket descending, and we can take the data that we got during simulation to train our models using neural networks to come up with better predictions for testing. But yeah, that certainly is not something that was covered today. And if you do have interest in having more conversations with that, please let us know. Yeah, I worked a little bit on this, so I'd be happy to talk to you about this.
There's another question about industrial scale deployment, and I want to say hello to all the attendees here today. Thanks so much for your attention. I'm Matt Bauman. I lead sales engineering here at JuliaHub, and I can field this one. Industrial scale deployment means lots of things to lots of people. We're continuing to work on how to best deploy Julia, especially with the upcoming 1.12 release with Julia C for compiled workflows. That's often how folks think about industrial scale deployment. You want to compile to an executable that doesn't need a runtime. And so that is really where a lot of our energy has been going during this latest release cycle. But even without that, we have teams using Julia and Modeling Toolkit and Julia Sim in production today. It's not too bad to set up in many cases, but again, depends on your requirements in terms of security, deployment target architecture, your CI/CD workflows, all of those things. So if you want to learn more about that, please don't hesitate to get in touch with any of us on my team here at JuliaHub. And thank you so much, David. This was a great presentation, and I appreciate all the feedback from folks throughout. Hopefully, I was able to answer the questions as they arose during this. But we have a few more minutes here in case anyone has some last things. Well, with that, how about we bring this call to the close? Thank you so much, David, and thank you everyone for being a part of this.
Thank you.
All right,
And
thanks a lot, everyone.
we'll email you the record version of this workshop so that you can view it at your convenience. And for future webinars, you can visit our website in the events section. We have a couple of more webinars and workshops coming up, and look forward to see you there as well. Thanks a lot, David, and thank you, everyone.
Thank you.